Thank you for coming. Very excited to be here. Going to have two talks this weekend. This one is on the Sapphire Project and how we've been moving into Phase 2. And I forgot to bring a picture of Phase 1 so you could see our humble beginnings. The Sapphire Project is a project to try to reproduce electrical cosmology, to look at how electric fields and currents manifest at a cosmological level around planets, around stars, in the galaxy. It's extremely ambitious, but very exciting to be working on. And I will just jump right in. There's the core team. That's the new chamber. That's the day the new chamber arrived. We actually found it in someone's backyard not far from here, which is interesting. And then we transported it on a flatbed several thousand miles to eastern Canada. And that's our picture there, welcoming the new chamber into the lab. Here's a schematic design view of the chamber. That center cylinder is about as big as a car. And if you stand there, your head is about at mid-level of the chamber. And here's looking down from above. I'm not going to go through all these pieces and parts of it, but we have a wonderful suite of instruments, mass spectrometry, spectroscopy, visible light spectroscopy, UV, infrared, a lot of instruments hanging off that, a lot of vacuum pumps. It's kind of like a fractal sometimes. The closer you go into the chamber, you just see more and more complexity coming out of it. I just took a picture here of our cryo pump, which allows us to get to very low vacuum pressures in the chamber. And it's pretty exciting having a thing that's only a few degrees above absolute zero sitting right next to you. And then here is a picture of the control room. That's where we collect all the data that we're taking. It's where we control the chamber. All the controls for the chamber are in there as well. So just a quick list: optical spectroscopy, mass spectroscopy, Langmuir probes, UV cameras, IR cameras, high-speed video, radio antennas, pressure, voltage, and current control, and real-time changes of geometry. So as you can see, we have had a lot of work we've been doing this last year is getting all of that to work together. It's an enormous undertaking just to get all those different pieces working and have them all work together. So let's jump right into some plasma physics and some astrophysics. Here is a picture of a discharge in our chamber. You can see the center sphere there is dark. That's a metal anode. For those of you on this side, right there, that's one of the electrodes. And then around that is a plasma discharge. We vary the electrical factors inside the chamber to get different types of discharge, is the general principle there. And this one, we wanted to put in a sphere with a magnetic field around it. So that's a simple dipole magnet inside that sphere, because one of the things we want to do is be able to study planets and stars which have a magnetic structure similar to this. So the Earth has a north pole and a south pole. We want to put in a sphere in our chamber that has a north pole and a south pole so we can study some of the physics behind that. So I made a sketch there you can see of, on the right-hand side, that center yellow part is the sphere, and then the red lines are the magnetic fields. Just a sketch of how the magnetic fields are around that. The alternating light and dark bands that you see are the point of interest here. Those are called electrical double layers, and you're going to be hearing a lot about those in astronomy over the next decade or two. While they've been very well known to laboratory plasma physicists, electrical engineers, etc., the electrical double layer has had a very difficult time getting any traction in astronomy. And this is because for most of the 20th century, the most influential astrophysicists have considered that large electrical structures, such as those, are impossible in outer space. So no one went to look for them, and no one designed instruments to measure them. And yet, every place we have put a satellite, around our own planet, around other planets, out past the boundaries of the solar system, between our planet and the sun, every place we put a satellite, we find electrical double layers. So they are truly ubiquitous cosmological electrical phenomena. And so one of the purposes of SAFIRE is to systematically study double layers so that we can give back to astronomers a better toolbox, so to speak, to examine the cosmos around us. So what is a double layer? An electrical double layer is like a battery or a capacitor, but it's not. But it's like those in the sense that there's a separation of charges. So here's a little drawing. You can see on the two planes there's positive charges on one side, negative charges on the other side. And then there's strong electric fields in between those two, because if you're a charge, you will be repelled by one of those walls and attracted to the other wall. Double layers can store energy because it takes energy to make them, so they have energy in them. They can transport energy. For example, we see a steady stream of double layers coming out from the sun, carrying energy from the sun. Double layers can also transform energy. For example, in a planet's magnetosphere, above our own Earth, for example, double layers are stepping up the energy of electrons from kilovolts to megavolts. So one of the things these do is vastly increase the energy of charged particles out in space. Double layers can also release energy. They can explode. And exploding double layers, I think, is another name for magnetic reconnection. And if anybody here could help me make that connection, I'd be very grateful. The whole idea of magnetic reconnection is based upon mathematical simplifications that don't really make sense. They don't really describe nature. And yet that's the theories we have now as a community. So we're trying to explain phenomena, explosive phenomena in space, and we have to call it magnetic reconnection. But I'm convinced that what's really going on is these double layers are forming and exploding. But I would like some help putting that together, if anybody here could help with that. Double layers also emit radiation, broadband electromagnetic radiation. They produce the aurora kilometric radiation that comes off of our Earth and the decametric radiation that comes off of Jupiter's magnetic field. So as I said, they are a ubiquitous astronomical phenomena. So coming back to the discharge in my little drawing, I put the white lines in there to show where the double layers are. And so there's a special relationship between the sphere, the magnetic fields, and where the double layers are. Each of those light and dark bands is where charges have been separated, and you can see a bright glow because charged particles are accelerated through those electric fields, and they excite atoms in the plasma, causing those atoms to emit radiation. So coming back to the diagram, you could imagine this wrapped into a half sphere and then have several layers of this, one on top of the other. Multiple double layers is nature's way of handling large changes in voltage. Nature very seldom will accomplish a voltage change all at once. As we look around and study how she does things, she tends to break things up into steps. So, for example, in the Earth's magnetosphere, I drew little, that's the Earth in the middle, the Earth's magnetic field around its side, and then I drew little plus and minuses along the field line there, indicating what was found. Again, kind of a surprise to astronomers because they don't have double layers in their toolbox so much. A satellite flew through at just the right time to measure not just one but thousands of double layers right next to each other, each about 30 volts, I think. And they were traveling really fast, about 3,000 kilometers an hour. And the electrons that started at the top had about kilovolts of energy. The ones that came out the other side had megavolts of energy. So for some reason, the Earth is doing this. It is setting up these accelerating engines inside of it that boosts up the energy of electrons above our heads. The reason it was a surprise is because, as I said, theorists really have not had this in their toolbox. They have to try to explain these things in terms of shock waves, plasma acoustic waves, magnetohydrodynamic equations, and whatnot. And the solutions they kept coming up with were very complicated, and they had really unrealistic starting conditions for the electrons and protons up in the atmosphere up there. So just so you can, that might have been a bit fast, but to appreciate, so right out of the box, the Sapphire Experiment, we put our pseudo-planet in there, fire it up, and right away we are reproducing electrical structures that have been very controversial and not so well known around our own Earth. If we could have done this experiment, for example, back in 1980, and we could have published the results, and if astronomers would have read that, then they would have gone up into space looking for these structures rather than being surprised that they find them. So this potential for cosmic structures to inform our experiments and our experiments to inform astrophysical explanations is the main purpose of the SAFIRE project. For example, in addition to traveling double layers through the magnetosphere, there are also double layers above the north and south poles of our Earth, closer to the Earth. Those accelerate charged particles, giving us the aurora borealis. Do these move also? We don't know. What are the required conditions for their formation? We don't know. Do they always accelerate particles, or do they slow them down also? We don't know. Are they only a DC engine? Do they only work increasing one way, or do they also have alternating current properties? Again, we don't know. So this is what SAFIRE is doing, is asking these questions, getting some experimental data, rather than jumping to what theory says should be happening. Another example of how this plays out cosmologically speaking, in the center there, that's, for example, Jupiter. It could be any planet. And then that band around is either where the moons go or the plasmasphere around the planet. And there's connections. There's lines being drawn from the planet out to the moon, for example. We know that there's radiation coming off from those zones that connect the two, especially if you connect from the Earth's pole to one of the moons of that planet. We know there's radiation coming off of them, but if you go to the journals, it's always, we're not sure why the radiation is there, we don't know the mechanism, etc. So we know from our own work that double layers produce radiation. And there's a great team of scientists up in Norway and Sweden that are the students of Hannes Alfvén, who also have been continuing this tradition of studying electrical structures in space. They have been telling people for decades that double layers produce radiation. Go look for them around planets. So once we can determine experimentally the electrical conditions that are necessary, then we can learn a tremendous amount about places that we cannot put a satellite. So, for example, we're not going to be putting a satellite tomorrow into a solar flare. We're not going to be putting it into a pulsar. We're not going to be putting it into active galactic nuclei. We have to study those things from a distance. We have to look at the radiation they give off. And so if SAFIRE can elucidate the nature of what radiation comes off depending upon what the conditions are where it started, then we can look back at past astronomical data and reinterpret it, and we can also give direction for future astronomers, future satellite builders. Hey, go look for this, or build your machine so it can observe this. And this summer, we'll be running experiments to determine what I just said, the characteristics of double layers, what they emit, how to form them. Another example in the astronomical world is something called fast radio bursts. Now, these are millisecond bursts of energy that are measured by radio telescopes, and there is no agreement about what creates them. The signals have a high dispersion measure, which means that the different wavelengths in the signal have been spread out a lot, which means that the light has to have traveled through plasma. Now, they could be originating very far away and traveling through the intergalactic space, which has a very undense, what's the opposite of undense? Tenuous plasma. And so you would be going through a long distance of a very thin plasma. But there's also, they could be originating very close to us, these bursts, and traveling through a very dense plasma. And so the dispersion measure doesn't let you know which of those is the case. it's been assumed up to now that these bursts of energy coming from the cosmos are very far away. Now, to account for that, how they could make it to us with so much energy, you have to have a very energetic event if it's that far away. And if you only have gravity in your toolbox, then you have to have these enormous train wrecks happening out in the cosmos, like a neutron star colliding with a black hole, and they're both on fire, and they go crashing off a cliff. And that gives you the amount of energy you need for this burst, right? But there seem to be about 10,000 of these fast radio bursts every day, so it's pretty unlikely that we have all these cataclysmic events happening far, far away. It's my feeling that these fast radio bursts have an electrical origin, either the formation or destruction of double layers, but it's just a speculation on my part. Another aspect of what SAFIRE is doing is to better incorporate double layers into circuit diagrams. Something as simple, as practical as a circuit diagram is very hard to find in an astrophysical journal. Here, for example, is our current understanding of some of the currents that are going around the Earth. And as complicated as this is, okay, it's missing notable things like capacitors, resistors, inductors, etc. Now, on the flip side, if you go to an electrical engineering course, you're not going to learn about double layers because double layers don't form inside of wires. They form in plasma out in the cosmos. So it's time for these two worlds to come together. Our circuit diagrams need to incorporate double layers, and our astronomy diagrams need to have better circuit diagrams put into them. And if you're looking for one book to go to study how electricity manifests in space and in plasma, I have to recommend Anthony Peratt's book. Just had a new version come out. So the next part I'm going to say is basically out of Mr. Peratt's book. It's very applicable. So since double layers form in electric currents, the double layer itself has to be considered an element within the complete circuit. And this diagram represents a very simple series circuit with current flow. We have a generator, a motor, a resistance, inductance, and a double layer. Now, if the electrical potential in this simple circuit is increasing, that means the generator is transferring plasma power into the circuit. If the electrical potential of the circuit is decreasing, then we have a motor transferring energy into kinetic energy of the plasma or into electromagnetic radiation being emitted. The circuit also has a resistance, which dissipates power into heat, and an inductance, which can store energy. In most cosmic plasma situations, the individual circuit elements have to be replaced with elements that are distributed over long cosmic distances, such as the well-known currents between Jupiter and its moon Io. It's simply to say there's things going out in space that are electrical of nature. We have to capture them into circuit diagrams. Now, every circuit has an inductance, which you will not find, again, in most astronomical thinking. An inductance, if a circuit has inductance, that's intrinsically explosive. Okay? The inductance energy can be tapped at any point along the circuit. And any interruption of the current flow can transfer all of that stored energy to be released at that one point of interruption. It seems as though the one point where that eruption happens is at these electrical double layers, which then release enormous amounts of energy, or at least energy proportional to the potential and the current in the circuit. And that energy can be used for accelerating particles or emitting large amounts of radiation. So the double layer's role, its ability to store and explosively release energy, will be central to interpreting a wealth of data that is coming back from infrared telescopes that we've put up. They've changed the way that we see our galaxy. They've changed the way we see star formation. This is an image from one of the infrared, I don't remember if it's Spitzer or Herschel telescopes. That's a filament of dust that's glowing that you see. And it seems like all stars form on these filaments. Now, in a gravity model, in the gravity model that we've had for the last 100 years, it's impossible to form stars on filaments. And now we put up these infrared telescopes, and we're seeing that all stars seem to form on these filaments. What are these filaments? We don't exactly know. We're studying them. There's strong reason to suspect that they are current flows, the flows of current at a galactic scale. And those kinks that you can see that start to light up is where that enormous galactic energy can be broken, like I was saying, and all that energy can be released. Now, is it released to form a star? Is it released to do other things? We don't know yet. But I'm just saying that this is one of the things now that what we learn in the SAFIRE experiment will give us an enormous amount of information that we could take back and look at these images again and see if we can understand them differently. So I just want to say that, make sure it's clear to everybody, this is a team effort. I'm part of a pretty amazing team. Tracy Childs, who's not in this photo, she keeps the business side of things working really great. Monty Childs has been leading the project for years now and gotten us through some very difficult times. You could imagine a project like this is not without challenges at many different levels. Lowell Morgan brings about 50 years of plasma experience in the laboratory to it. Paul Anderson is a chemist with expertise in high-energy reactions. Jano Onderko, he heads up the instrument control, integrating all the data and all the instruments. Jason Lickford takes all the blueprints and he turns them into actual physical devices. And Leighton McMillan is a machinist who also handles a lot of the electrical aspects. Jim Ryder in the lower right-hand side there, he has decades of experience leading very large aerospace projects. And so he helps tremendously in keeping us informed both about what was going on with past satellite missions and about what new satellite missions NASA, JPL, ESA are working on. Scott Mainwaring on the bottom there also, he has been providing financial support for years to the project. He actually was one of the people who got the project off the ground. And Bruce Mainwaring, his father, also provides financial support and has been doing his own work for decades looking at electrical aspects of Earth science. So the team is currently writing up a paper from our experiments last month. We're taking our data for our next paper, and if everything goes well, this should be a pretty exciting year for some new foundations being laid for astronomy. Thank you.